learning focused on neural architecture search back in 2015 to 2019. Neural architecture search, very quickly, is the process of searching for the optimal structure of a deep neural network. So think about GPT, for example, that has a certain kind of structure within it. That structure is designed by hand, but it doesn't need to be. You can search for the optimal structure, but the computational cost of doing that is absolutely enormous, because you take the computational cost of training a model and then times it by however many times you're kind of testing it for the search, and it just becomes ludicrously large. Kind of long story short, that led me to a pretty deep understanding, an uncomfortable understanding of the problem of compute within machine learning. Now, obviously, I co-founded Gensyn. Gensyn's a machine learning compute protocol. The long-term goal is to be the network for machine intelligence. The shorter-term goal is to connect up all of the machine learning capable compute in the world. So GPUs, TPUs, CPUs, anything that's capable of doing ML operations, and allow those devices to be used just on demand programmatically. So instead of going to AWS or Google Cloud and booking time on a specific GPU, you're just defining a model and then sending that model out to be trained. And it might train on one device, it might train on 1,000 devices, it might train on one NVIDIA H100, it might be 1,000 MacBooks. You shouldn't care as a kind of developer, you just want to pay for ops, basically. So that's the protocol we build in the first instance.
Thanks, Ben, for the intro, and also thanks for coming here today. So I guess for someone who is involved deeply with the training processes and approaching this compute problem from the training angle, I think it would be very interesting to reflect on the recent update, especially when it comes to OpenAI's O1 model, because it seems that a lot more emphasis recently has been placed on what happens post-training. On the inference side of things, there is also expectation that it would take relatively more compute than it used to compared to training side of things. So just curious how somebody from your position perceives these changes, and what sort of second order effects you think this sort of, if this is even important shift, what sort of second effects it would produce?
Yeah, I think it is an important shift. I think the sort of inference time changes that happen within the new O1 model are particularly interesting. You can think of them as just optimization of the sort of read query portion of machine learning, where at Gensyn we often think about just kind of from first principles what's happening within machine learning, and kind of naively and simply you can think about it as just compression. You're essentially taking rich real world data coming from sensors and things like that, so images, video, audio, text, whatever data you want, and you're compressing that down into this shared space, which is just a matrix, basically a huge matrix that compresses all of that information and allows you to interrogate it in a much richer way than we had before, where before maybe we would have to manually describe something into text to store it in a database. Like in Wikipedia, if I wanted to sort of store information about this room, I would probably write a load of text about what I can see right now, and then I'd store that in a database. Whereas with machine learning, we can take a lot of sensors in this room, we can distill that down into a space, and then we could generate out images or video or audio of the room, or text if we needed it, and then we could kind of tweak that. So it's much richer interaction, but at the end of the day, it is still just kind of compression, just being done by machines. The changes with O1 are basically changes about how you kind of interact with that compressed data, which are great because they improve our ability to interact with it. So basically recursively calling the space, the compression space over and over again, you can extract better information out of it, you can sort of prompt it better, you can learn more how you can get value out of that space. But from our perspective, that's just an optimization on top of the read portion, but there's still the kind of storage portion, the training part is just as valuable, if not more valuable long term. So I think we'll go through various phases where we'll optimize the read portion because lots of people are doing reads right now, then we'll optimize the fine tuning portion, which is kind of updates, and then we'll optimize the training portion, which are the original writes, and it'll just kind of keep going like this, where we'll have different waves for each of the different sort of fundamental operations you're doing on top of what is essentially just an automated compression mechanism.
I remember, I guess, about 1 year ago, I read one of the very interesting pieces written by Gensyn team, and I believe over there you explained the thesis why focusing on training, and essentially I think one of the main arguments was that with the training there is a significant flywheel, and you have this process of reinforcement learning as one of the important kind of inputs in this flywheel effect, and you elaborated well on the thesis why training is the biggest opportunity. I guess this conviction is not not shaken by this new change in more focus on inference?
Yeah, not at all, really. We think these things will happen. We have a very long-term view. And so within our long-term view, we look at kind of analogous situations. And one analogous situation is the internet as it developed. And so early on in the kind of life cycle of the internet, we thought that it would be read-heavy. So there'd be a small number of websites that like businesses would create, and then everybody would just be reading from those websites. But very quickly, we moved to the kind of GeoCities era where people wanted to create their own content. They wanted to put information out there as individuals. And then we moved even further into social media, where now the vast majority of the content of the internet is actually created by individuals. Early on, that wasn't the case because the costs and the ability to do the write itself for the individuals to go and put the information out there were too high, and the UX just wasn't there for it to be done. So it wasn't necessarily that people weren't going to do it. It just wasn't, the mechanisms weren't quite right. The fundamentals weren't there to allow people to do it. Once they were, everybody did, and it kind of forced that into happening. We think the same thing plays out here. At the end of the day, the internet itself is just essentially like a huge stored knowledge base for humanity. It's our way of interacting with each other, but it's also our way of storing information together. And we view machine learning as a fundamental change at the low level of how the information is stored, but it'll still operate in the same way. We're still all individuals contributing to that shared knowledge base. To contribute to it in the machine learning world, we have to train. We have to update weights. We're not just going to be reading from those weights. So I think the sort of focus on inference, to me, is that sort of similar short-term focus as we had in the early days of the internet, where everybody says, well, everybody's reading right now from websites. We look at that and we say, well, that's because the tech isn't quite there yet to let everybody write. But when it is, they will.
Makes sense. And now I would like to jump on the more crypto-specific angle. I guess it would be good for audience also to hear the motivation for, in general, just approaching the AI technology through crypto approach, through crypto lenses, and what was kind of the core drive over there.
Sure. So again, kind of thinking from first principles a little bit, we again look at the kind of origins of the internet, and so the protocols, not in the Web 3 sense, not in the crypto sense, but protocols just in the sort of open standard sense that sit underneath the internet. And there was a kind of period of time, the protocol wars, when we were figuring out as humanity what those were going to be, and some companies tried to capture them and make them these closed source things, but in the end what won out was TCP/IP, so the internet protocol stack that we have today. And that stack's allowed us to have this open communication mechanism that we can all opt into and that all of our devices adhere to, and it allows us to just communicate with anybody without necessarily having to go through gates of different companies. It's the kind of most open thing that we have. And then we think, well, that's incredibly open and incredibly efficient. We've got these changes in the base technologies that sort of emphasize a different thing from communication. So the communication protocols were required just to allow us to all speak without talking different languages, basically. But machine learning requires another base resource. It requires computation to execute. And that computation right now is in a similar place to communication was back before the IP stack was decided. It's lots of different companies all with their kind of own specific way of doing that computation, but that doesn't need to be the case. We can have a kind of open standard way of doing that computation, and if we did, we could create a similar situation that we created with the internet, but over computation, which is now the kind of big limiting resource. So to us, it was looking at how do we solve this in a similar way to the internet? How do we make it as large as it could possibly be, put no kind of limiting factors on it, and how do we make it persistent through time so it's not dependent on a single company? And to us, that came to the kind of answer of crypto protocols. So we could build essentially open source technology that wasn't limited by a centralized party, and specifically the limitation would be trust. So if we want to connect up every single device in the world, we're going to have to solve the trust problem of how do we know that each of those individual devices is actually doing what has been requested of it. And if you were just thinking as a normal centralized company, you would say, well, we just KYC everybody. But the cost of doing that is enormous. The human cost, the kind of monetary cost, computational cost, et cetera, it grows really fast and it puts a limiting factor on top of it. So we want to make this just open. Anyone can run it, any point in time, fault tolerant. Every device can be executing it. But we want to know whether people have actually done the work. And the only way to do that so far is to have crypto protocols behind it. So you have decision-making via consensus. And that allows you to have a trusted third party in a dispute between two parties where in a dispute between two parties, the only way to solve that dispute is with a trusted third party. And crypto gives us that as a consensus over a group. So that was the kind of thinking behind moving into the space for us. We needed that consensus mechanism. And then from there was lots of work to figure out how do we take a gnarly machine learning task that's state dependent and non-deterministic and massive and distill that down into something that can actually be arbitrated by a consensus mechanism. So how can a load of nodes executing the same thing actually prove that a large-scale ML computation has been done without the overheads being ludicrously large? You can imagine if you trained a neural network on Ethereum, it would be like obscenely expensive and impossibly long running. But if you can distill it down into a small piece, then you can kind of prove that computation, and that's something that Gensyn's been working on for a very long time.
And today, usually when people talk about Gensyn, they tend to position Gensyn along this category of GPU networks, and it seems that this category also kind of includes many other projects that are in fact quite different from Gensyn. Some of them started much later and were much faster to go public with the network and so on. But can you just elaborate how do you dissect this current very large category of GPU networks, and why actually the problem set is much more challenging, that it requires this patient approach from Gensyn and building for the past several years, and what sort of problems are being overseen by many of the others that are already kind of live with quote-unquote GPU network approach?
Sure. So there'll probably be a bunch of generalizations in what I say, and obviously I'll be biased given what we build, but I'll try and kind of explain from our perspective. So the easiest way of, I guess, understanding the difference of Gensyn with some of the more kind of front-end focused GPU networks is that long-term focus that I mentioned. So we have a very clear vision of what we think the world of machine learning will look like, and it goes to those kind of base principles of being this compression mechanism that can be applied everywhere and can change the way we interact with data, and we would just want to enable that to happen as fluidly and as at a larger scale as possible. And so that means we build for that. We don't necessarily build for the way people currently access machine learning compute or the kind of actions they do right now. In the contrast, a lot of the current GPU networks do build for that. So they take the kind of current situation of the market and they say, well, if somebody wants to train a machine learning model, what do? They go to AWS or go to Google Cloud. They go into a kind of interface and they select a type of GPU. They select how long they want that GPU for, and then they kind of rent it, lock it down, and SSH into it, and train their model, etc. And the GPU network, a lot of the other GPU networks will take that and say, okay, if we decentralize the back end of that, we can get a cheaper price on the supply, and we can disintermediate those front ends, which is true. I think if you can decentralize the supply, you can increase the supply side liquidity of machine learning compute, and you can bring prices down. But to us, that's a kind of small optimization on the market. It basically gives you a slight edge against a centralized player where you have slightly kind of cheaper resources behind you, but you're essentially doing the same thing. And so we think that kind of fight will go on for the next couple of years. There'll be decentralized networks, there'll be centralized companies who, for whatever reason, are able to subsidize for longer and compete on price. Maybe they have a cheaper source of compute because they're closer to NVIDIA or something like that. There's lots of kind of reasons why you can bring your costs down and offer cheaper compute out to people in that same way. So we thought about this quite a lot 4 years ago when we were first looking at this problem, and back then the centralized compute market was heavily constrained, so prices were very high. It's interesting that over that kind of 4-year period, the centralized market has got very competitive, so prices have been driven down heavily just from the centralized providers. That kind of brings down the opportunity a bit for those decentralized front ends, because what are you competing on? You're competing on this base cost, but you have to meet them on UX. So you have to do all of the activities of those centralized marketplaces. You have to build the AWS style interface. You have to build the AWS style APIs for people to switch over, etc. And so you're you're diminishing this margin that you're available to take. And that's just not kind of what we want to do. There is still margin to be taken there, though, to be clear. It's a business that makes sense, but it's a percentage improvement on the current rather than a step change for the kind of world, which is more where we focus. So yeah, briefly, I guess, on us again, the goal is to bring us to that future where ML is just happening everywhere. It's completely ubiquitous. It's happening on every device, but the UX and how people actually interact with compute will change. So we're not building these front-end interfaces where you're booking time time on a GPU because we don't think in the future anyone will be booking time on a GPU. They'll be sending machine learning ops somewhere, and they won't even really care where those ops are going. At the end of the day, the core resource of machine learning is electricity, and there's a refinement process that goes on with electricity to turn it into ML ops, and then those ML ops are executed by someone. And currently there's a load of companies in that kind of stack, all extracting rent basically from doing different portions, and we think actually you can commoditize ops and you can go much closer direct to the devices themselves, to the refinement process of electricity, and that's the goal of Gensyn as a protocol, is to kind of disintermediate all of that and just provide basically a liquid market of ML ops to anyone. There's kind of burst scalable, there's a fair market price, there's accessible on demand, crucially accessible programmatically, so rather than just people doing it, machines themselves can interact with it, but that is a long-term view, as I said.
And beyond the focus of Gensyn, what are some of the other categories that you think are extremely important, for instance, for somebody who is looking to invest several years of their career into building new startup along the lines of crypto and AI intersection? Like, what would be kind of important problems that are worth devoting your time to?
Yeah, good question. We think about this a lot, and our attitude to it is we have that kind of long-term vision of the way ML is going to be, that sort of shared knowledge base future. Right now we're building the compute protocol because we think that's the most constrained part. We would love for people to build the other parts because it makes it happen quicker. If they don't, we'll do them, but later. But we'd prefer other people do them right now. And I think the best way of thinking about it from our perspective is to sort of think from first principles again. So what are the core resources of machine learning? Compute is a big core resource, but data is a core resource as well. Expert knowledge in the design of models is a core resource. That's coming from humans right now, but it also heavily comes from machines themselves. That my research was to kind of get it from machines rather than from people. And then labeling. So humans providing context around data points. That's another kind of core resource that can be incentivized in some way. And so I think building the stack, maybe it's a protocol, maybe it doesn't even need to be a protocol, but building the tech to allow those things to be accessed by people and ultimately machines, I think is a really interesting place to start. There's a bunch of people looking at the data problem. I think there has been for a while, but so far we've not seen a sort of clear alignment with that vision of the future that we have for incentivizing that data collection. But yeah, I think looking out into the future, we think there's been a huge focus within machine learning on taking the internet as it stands up to a certain point, which is basically structured data that we've all been labeling for decades. And so in many ways, like OpenAI got a quick win with it. They were able to take like decades worth of like carefully structured labeled data that we'd all been creating into the internet, and they were able to compress that into a model and have amazing gains. But you don't really get to do that again. You can make it more efficient, but you're using the same data basically. So the next big challenge becomes, how do you make that live? How do you do continual training on top of these models? And that continual training piece has to go out to the individual. It can't go and collect data from one centralized point. It needs to be collecting live data from the sensors that exist in the world. And so I think one particularly interesting thing to look at is the incentivization of us all to be contributing data to the kind of live world model. So when we're interacting with these models, when we're asking them questions, instead of them answering up to last Sunday or whatever when the model was trained to, it answers with real live data. And if it doesn't have that real live data, it could incentivize somebody to go and fetch it. And I think that's all possible with crypto as a technology. We could have this incentivization of essentially creating this huge decentralized digital twin of the physical world. It just needs all of the kind of rails to be built. We're building the compute rail, but the data incentivization rail, the labeling rail, the design of models rail, they all need to be built. And so if anyone's thinking of building those, please talk to us. We will happily share all of our thoughts on that with you. Like, we want it to be built quicker basically because it benefits us. For our vision to be achieved, we can't just build the compute protocol and then sit back and wait for the world to realize. We have to kind of actively incentivize other people to build the other pieces. And so we'll happily share all of the kind of thoughts we have on design with anyone who wants to chat basically.
And I think we have time for maybe one more question. And in this last section, I wanted to take a step back and just reflect on, like, in the historical context, how big some of these changes that we can expect to see in the next decade. I guess, like, 1 decade in a historical context is a very short period of time. So, for instance, in 100 years, when people reflect to this decade, the emergence of the new form of intelligence and potential societal and cultural impact that it would have, like, how would they reflect on it as a very positive period in the development of civilization, society, or like what would be kind of optimistic or pessimistic scenarios, and where would you kind of think we land in the next 10 years?
That's a really good question. I think it's still to be determined which path we go down in terms of what we'll look back on. I think the biggest thing, kind of the whole of society will look back on, is the way that we made certain kind of society level decisions about this technology. And I think that most clearly comes down to, like, regulation and legislation. And so how did we limit this technology, and how did we allow it to flourish in as open a way as possible? Obviously, lots of opinions on how people will look back on kind of how infrastructure develops and things. But I think realistically, most people won't look back on how the infrastructure developed. That'll just be something that happened. What they'll look back on is, how did we all relate to AI? And I think we have the opportunity now to let it flourish in the way that the internet did, but we also have the opportunity on the kind of negative side to force it into this kind of condensed situation where only a small number of players can actually apply it as a technology. And if we do that, I think we'll concentrate the power that comes from this technology with a small group, and we'll create really negative outcomes for the world. I think we're in this sort of decision point where we were with social media, where we could hand this technology to a group and give them outsized power on deciding what we all think, essentially. Like, if you think about the human kind of knowledge base that we described in the internet, if one company gets to decide the biases that go into that knowledge base, they basically get to decide what we all think. If we're talking to kind of ML models all of the time, and we're getting kind of our information from them, we're reading resources through RAG through them, we're kind of querying the rest of the internet through them, then it becomes this lens that if you control the lens, you control the kind of like thoughts of people. And I think that's really dangerous. I think we did that with social media. We're seeing the outcome of that with the kind of censorship on social media platforms. Censorship of social media platforms is essentially controlling the thoughts of the population. And like, Jack Dorsey's got loads of thoughts on this. You see him talking about how he wishes they'd built that as an open protocol. I think we have the opportunity now to enable machine learning to be built as open protocols. If we do that, I think we'll look back very favorably, and we'll say, yeah, we made the right decision there. We allowed the internet to happen again, but with new primitives, which are really exciting and powerful. If we don't do that, if we lock it down, we'll look back and we'll say we let Facebook happen again. We let somebody capture human consciousness, but in a much more extreme way than kind of Facebook did, which I think is quite dangerous. So the biggest thing I think people will look back on is the legislative kind of moves we make. And we're not fully sure what that will be yet, but obviously have biased opinions, as you've heard.
Well, we are all hoping for a positive scenario. Unfortunately, we don't have that much time to discuss in depth all of these very deep topics, so we'll have to close here. But I hope you guys enjoyed the conversation. I believe Ben will be around for one more panel, and probably going to stay around after the panel if somebody wants to chat about the topics he just touched on. And thank you for listening.
Thank you.
Thanks.
Nice one, man. That's good.
Yeah. You're staying, right?
Yes.
Okay.
Yeah.